Okay, let's cover Castigliano steering beam examples. So I apply a load P. I want to know maybe I want to know what the deflection is at point P. Then you take the derivative u respect to P and you get the deflection. Okay. If I want to find the how much slope I get towards the end of this, I put a moment there, maybe a fake moment. Partial u respect to C equals the slope there. Is that clear so far? Yeah? You want me to just do a quick example here so you can see how cool this is? Just really quick. It takes like 1 minute to do it. So much fun. There's a beam, load P applied. I want to know what the deflection is at this point here. Ready? Step 1, cut. What is the moment here now? Good news. I can use any coordinate system, so I'm going to choose it like this, x. What is the moment? P times x. So what is the energy is integral m squared 2ei equals integral, what is m? P squared x squared 2ei dx. What is this integral? P squared L cubed 6ei. What is the partial u respect to P? Isn't that the deflection there at point P? What is that derivative? PL cubed over 3ei. Isn't that what somebody read? There's a gentleman here that stated it. I think somebody here stated it. You stated it. You Googled it. It was P squared, P L cubed over 3ei. I got the same answer. Agreed? Did you get the same answer? What if I want to know what the slope is at that point where I apply the load P? I want to know what the slope is. What will you do? Put a fake moment C. Let's look at this cut there. What is the moment there? C. What else? C plus px. Ready? Next. What is next? U equals integral 0 to L C plus px squared over 2ei. Huh? Dx. Partial of u respect to what? What I'm interested in? The slope? C. So partial C. At C equals 0. Integral 0 to L. Let's do it quick. To px plus C. This is getting dangerous now. I have to use my memory on how to do this. I think it's like this. Px plus C divided by 2ei dx at C is 0, no? Am I doing the derivative correctly? The 2 cancels out. I think that's it. So C equals 0 means D is 0, right? So now the integral is just P, what? Px divided by EI? Isn't that it? What is that integral? That's easy. That's P squared. No, that's not P squared. It's P L squared over what? 2EI? That's what I get? Is that the slope? Theta? That was it. We did it. It's done. I don't know if it's right. Somebody should check my math. Do you guys get how this works? Easy, huh? You can add that strain energy for all loads. You can have an axial load, a moment load, a shear load, a torsional load. You can add them all up. You can have a very complex problem that has shear, bending, tension, whatever you want. You can add them all up, okay? And then you can find the deflection using that derivative approach I showed already several times. You can take the derivative the load respect to pi to get the deflection. So if I have a load, apply pi, take the derivative with respect to pi, and that's the deflection at point I. If you want to know the slope, similar process, take the derivative with respect to the moment couple. That's whatever it is, and that gives you the slope there. Okay. Question there? Where? Yeah, that's a shear one. And alpha is a correction factor that I provided here. A correction factor there. Q is the moment of area, if you recall. We did an example. B is the width of the beam, I is the inertia, moment of inertia, A is the area. I don't expect us to do a problem like that. That's more useful for like if I cover Timoshenko beam, where shear starts becoming like if you have a very thick beam, then now you have to account for shear forces. But when it's thin beams like these ones, then the shear effects are small. So we're not going to do any problems with that here. But if you do take one of my advanced courses, as you can attest, we'll be covering that. Here, the question is, what is the slope of this beam at point A? That's the question. So if I have a load P applied, like you see here, I have a distributed load P applied, I can get the reaction forces, but it's asking me what is the slope there? So I can add the moment couple like you see there. And then I do, what can I do now? I can get the moment here and the moment here. And again, I repeat, I get the strain energies quite easily. So I did that. I don't want to bore you because you know how to do, how to find, everybody knows how to find reaction forces from statics. Yeah. We should know how to do that, reaction forces from statics. Then can I do a cut now there, huh? And then I can calculate the moment in section number 1. This is section number 1. This is section number 2. So section 1 and 2. I can find the moments in each of those sections. Is it fair if I just kind of show you the steps and you can just try it? Yeah, is that fair? Because this is covering statics, right? The part that's new is strain energy. That's the only part that's new. So calculate the moments just as you see here. And notice that these integral limits are important. The integral for the energy is going to be 0 to L, and the energy for this one is going to be L to 5 over 4L. Be careful there when you do your integrals. Because this moment here, M1, is only for this section, while M2 is for this section. Is that clear to you guys? Is that clear? Yes? So then, if I want to find the slope, guess what? I find the M times the derivative of M respect to C1. If you're worried about how I did that, let me just derive it for you again. Theta equals the derivative of M respect to, energy. I apologize. Energy, the derivative of the energy U respect to M. C, I'm sorry. And that's equal to what? 0 to L, derivative respect to C of M squared divided by 2EI dx. And that formula here comes from there. You can try it at home. Fairly quick is what you get there. Because EI is constant, it's not a function of x. So you can take that out of that integral. So that's what you get, chain rule then. And I did it here for you guys. I want you to try it at home. And when you set C equals 0, remember that C was fake. Just keep it to the very end. Get the derivative with respect to M, with respect to C there. Take that derivative like I said there. Okay, this derivative, do that derivative, and then set C equals 0. Don't do it before that. And once you do, you get the slope at that particular location here, which is a pretty neat problem. I think it's a very cool problem. Very cool problem. Any questions you have on what I did there? Is it simple? Do you kind of follow it? Let's do this one. You love curved beams, don't you? How many people love curved beams? Especially the elasticity area stress solution. You probably don't like me anymore. It's not my fault. It's the homework I got back in the day. But don't worry. We'll try to make the exam doable here. Here you have a curved beam, and I apply a load P. All you have to do is the same process. Do a cut arbitrarily. If I do a cut there, I get a shear load. I get a force that's normal to that section. And I get a moment there. So if you take moments of that point O now, that shear force goes to the point O, right? True? So does that shear force contribute to a moment? No? So I did it here. The moment about point O will give you moment equals PR, this load P times that distance R, PR, and that normal N times R, NR. So if you do summation moments about O, you get this formula. You also can notice that this shear force V is P sine theta, and the force N here is P cosine theta. I'll let you do the math. There's geometry, pretty much geometry. If this angle is theta, then this should be the shear and normal force. So the moment then is equal to PR. So if I plug these numbers in, these equations, I plug them into here. Okay, so PR minus NR, I plug it in here and I get PR times 1 minus cosine theta. Got it? Difficult? Easy? It's geometry, pure geometry. And you agree that that moment calculation is true all, if I do a cut here, I do a cut here, I do a cut here, that moment equation is the same. No changes. That's the moment for the whole thing. So now I can plug it in. I'll go straight. So take the derivative in respect to P now, because P, I'm trying to find the deflection at point P. So if I'm trying to find the deflection point P, then I have to take the derivative of the strain energy with respect to P. Therefore, I have to take the moment, the derivative of the moment with respect to P, do that, the derivative of V with respect to P, the derivative of N with respect to P. And so you can actually ignore the shear term if you want. You can keep this one here. But when you do the integral, now your integral goes from 0 to pi all the way to the left. Because I'm starting here. I'm starting on this end. So from here, theta. And so that's from 0. The integral should go from 0 to pi. And it should be d theta because I'm going all around the circumference, right? So when you redo this, don't worry about this term, the shear term. Let's assume it's thin, so you don't have to worry about that term. But this term I want you to keep because that term, you already learned what it is. That's the axial extension of that beam. And you know the formula for the axial extension already. We covered what that is. You don't have to calculate strain energy for tension load, right? Is that correct? We taught you what was the formula? P squared over 2EA or something like that? Remember that formula? Yes? Yes or no? You probably forgot now because we covered it a long time ago. But what is P here? P is it's actually not P, it's N. I should use N instead. So N is P cosine theta, no? Yes? So if I plug that in here, don't I get this equation here? Try it out at home and you will see. And then the moment, you're gonna get this when you do it. So when you integrate all this, don't worry about the shear term, neglect this term, you will get that this is the deflection of this beam when you apply a load P at that very end. Very straightforward. Again, all you have to do is calculate the energies. So you just calculate the energy. So U equals integral 0 to pi m squared over 2EI, d theta plus blah, 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 blah. And then you take the derivative of U respect to the one you're looking for. Here's the deflection P, the load at deflection P. So take the derivative of U respect to P to get that deflection, and that'll give you delta. Does that make sense? The kind of the steps that you need to do. And I think you'll be very pleased that everything will work out very nicely for you. Are you going to do the integral of 0 to pi cosine squared d theta by hand? Is that how you're going to do it? Where are you going to go to do it? Wolfram Alpha, Mathematica is free also through VPN, and also either MATLAB or I don't know, maybe chat GPT thing. Or hey, what is the integral of blah blah blah? Probably does it for you. Okay, yeah, it was done here for you guys. I have yet another example if you're interested, but now it's getting boring because now it's now I'm asking, hey, what is the slope of point B? Okay, just apply a fake moment there. Are you getting it? Are you getting this? Huh? Isn't this cool? Then you do a cut here, isn't it? Then you do a cut there. Then you calculate strain energy. I can make my coordinate system anywhere I want. I can put X there, right? And then I can do calculate the energy here, number 1 and number 2. Once I get the energies, I can add them up, and the energies are going to be moment 1, 2 over EI dx plus integral moment 2 over 2 EI dx. Right? Are you getting it? That's your strain energy. And then you can the derivative of U respect to Q, set Q equals 0, and that gives you the slope theta. You got it? You follow the steps. Was calculating moments in different sections covered in a different course? I know it was because I taught it one time. Okay, so it is covered. So go back and review that if you're not sure how to do that. Or you can review what I did, but I applied a fake moment in, like you see there. And I did it for you to be nice. So I actually didn't do it for you. It was in a book. So I cut here, did a cut there. The cut there gives you this moment. For M1, you get P times X1. For this one here, when you cut here, when you cut there, you get a moment 2 of M prime minus P L over 2 plus X2, where M prime is a fake moment we applied. Again, you find the derivatives. Like I showed, these partials are off. They're supposed to have a different symbol. Like the partial is not that's delta. So fix that, it's partials. Okay, does that make sense? That there's an error there in the book that I got it from. So take these derivatives, and when you're done, set M prime equals 0, and that gives us a slope. And because I got a negative sign, it tells me that the slope is going to go in the opposite direction of the moment applied. But if I got a positive, then the slope is the same direction as the couple that I applied. I have yet another example. Determine the vertical deflection of point C. Same thing, do a cut there, do a cut there, do a cut there. Find the boundary conditions first, of course. In this example problem, there's a load of 5 applied, but change it to P first. So change it to P, because that's where I want the deflection. Do the cuts for each piece. So I'll do a cut here, I'll do a cut there. So in this case, we have a moment 2 that can be quickly calculated. That moment 1 is this much. Find its derivative there with respect to P, because we're going to need that. And then for section 2, find the moment there too. And that section 2 we're talking about is this one here, right here. And then finally, I can now calculate the deflection there by taking the derivative of the derivative of the strain energy with respect to P. By the way, you don't have to use this formula. You can find the deflection in terms of strain energy. Take the derivative of strain energy with respect to P. This chain rule, you don't have to do that. You can do it the long way. And the important thing is you calculate the strain energy in terms of the load P. This whole chain rule thing is just another way to do it quick. But if you don't want to deal with this chain rule because it sounds mysterious, just find the strain energy for the whole thing, for section 1 and 2, in terms of the load P applied. And then all you have to do is take the derivative of U respect to the load P to get the deflection. And I did it here for you, and you get a deflection 16.4. With that said, I want to thank you, and I'll be seeing you very soon to cover failure theories. And I'll be here to take questions.